welcome to Wetlands, Geography 3850, Environmental Science 3000 at the University of Lethbridge. I'm trying a video this time so that you can see how nervous I truly am. I also have Finn sitting next to me. He's kind of under the couch, but if I can get him up, I'll show him to you. So today we're going to talk about wetland creation and restoration. You can see here this in the two photographs, you can see kind of the before when the wetland was actually disturbed and how they're digging it up and really kind of moving the ground around, and then what this wetland looks a number of years later. So we're going to talk about how these wetlands can be reclaimed and how what we can do to reclaim them. So this is going to be kind of an engineering type of lecture. Okay, so today's objectives, I just want to remind you to hand in your assignment 4. I hope you thought it was interesting, maybe perhaps a little bit frustrating as well, but I'd like you to hand that in and then we'll mark it as soon as we can. Please put this on the Moodle folder for this course. So today we're going to talk about the loss of wetlands and the recognition that wetlands have value. And this has created the desire to create new wetlands and to restore the disturbed ones. And in Alberta and also in many other provinces, there is a mandate by the provincial governments to actually restore these wetlands. And this has created a really viable industry, as you'll discover. So today we're going to talk about the terms wetland restoration and wetland creation, as well as the idea of wetland enhancement and self-design. And really the idea here is that we want to keep things simple so that we don't over-engineer these wetland systems. The next thing we're going to talk about is mitigating wetland habitat loss. So how do we reclaim wetlands in a way that we can maintain those habitats that have been lost over time? Third, we're going to talk about restoring wetlands, especially agricultural land and some of the forested wetlands that people have disturbed over the years. And then finally, hydrological restoration. So how do we make the wetland behave in a way that was similar to the way it behaved in the past? And sometimes this is quite difficult to do. So we're also going to talk about where to place wetlands in the landscape and how to select a site. Maybe the area that's being disturbed is too disturbed, so we might find an area that is proximal to the area that was disturbed in which we can place our wetland, and things to look out for when doing that. We want to identify and maintain proper hydrology that lasts for not only for when the wetland's being reclaimed, but for years and years to come. And then finally, we're going to talk about how to introduce vegetation and success. So what does success actually mean, and how long do we have to measure the wetland in order to know that it is successful, it's being reclaimed to the way it was in the past? So why would we want to reclaim and create wetlands? Well, it's really important because whatever land we disturb, we're affecting their ecosystem services. So we're changing the landscape in a way that maybe doesn't have the same services that it used to have, and maybe it doesn't have the same value. In Alberta, the province is mandated to reclaim and restore wetlands, especially areas that have been mined. So, for example, in the oil sands region, all areas that used to be wetlands that have been mined have to be reclaimed over time, and they have to be monitored. And there is a certain amount of policy that that needs to be considered in order to determine whether that wetland is successful. So, for example, a wetland could be reclaimed maybe 5 years after mining or 10 years after mining. Well, they're going to have to monitor it for another period of time. Maybe that's 10 years or 25 years or even 50 years to determine whether that wetland is successful. It's continuing to mimic the wetlands that existed there in the past. So as you can imagine, there's been quite a lot of research done on wetland creation, especially in urban areas, and also on wetland restoration, especially in places like the oil sands region. So in order to reclaim some of these wetlands, you really need to know the basics, which is a lot of what has been taught in this class. So the basics include an understanding of wetland science, an understanding of hydrology and biogeochemistry, and also how plants adapt to their changing environment over time and to succession. For example, in a number of wetland reclamation cases, what they're trying to do is they're trying to accelerate that successional process that might have taken hundreds to thousands of years to develop. They're trying to accelerate it such that the wetland mimics what was previously there within about 10 years. Now, if you've got an accelerating system, what that could lead to is that could lead to the wetland reaching its potential. It gets there, it's productive, but then it can keep going, keep going through the succession and move into an upland forested ecosystem within maybe 20 or 25 years, when really that wetland would exist for maybe another, several hundred years, all else being equal. So we need to know how this wetland responds to hydrology, how it changes in terms of its biogeochemistry, and what kind of adaptations are required. We also need to realize that as humans, we tend to try to make the best possible situation. We often can over-engineer things, but really with wetlands, they are simple environments in general. If you kind of dig a hole, a wetland will form. So we want to keep the design simple. And then finally, we want to focus on this idea of wetland self-design, where the ecosystem adapts and changes to its physical constraints. So if we set up the wetland to grow and form and to take up water and to develop over time, then we need to allow it to do so, and it has its own kind of way of designing itself so that it can be maintained. Now, if it starts to accelerate in its development, then we start to be concerned because, again, it could transition into a different land cover type. So some of the important terminology that we need to consider includes wetland restoration. This is the return of a wetland that has been disturbed or altered by humans to a previously existing state or condition prior to disturbance. So this applies to the case in the oil sands region where these wetlands have been disturbed and altered, and then we're trying to bring it back to the way the wetland was in the past. Wetland creations, we've talked a little bit about constructing wetlands and why we would construct wetlands, especially in urban areas. But this is basically taking an old land cover type or a different land cover type, such as an upland area, and then creating it or moving it into a wetland. So you're actually creating that wetland where a wetland didn't formerly exist. And then we have this idea of wetland enhancement. And this is where people increase one or more of the functions of that existing wetland. And so it makes that wetland enhanced. It brings out these functions, it brings out the utility of the wetland and certainly the ecosystem services as well. So how do we mitigate against wetland habitat loss? So here you can see, let me see if I can, oh, this is going to be real clever, guys. This is our reference wetland. Yay. Okay, this is our original wetland that we have that hasn't been disturbed. And what we want to do is we want to take this, I'm going to use a blue circle here, take the replacement wetlands. Here, this is the wetland that we've built to replace the original lost wetland, which I'm going to circle in green here. Okay, so the original lost wetland is basically the same as the reference wetland here in red, except that it was lost. It was disturbed in some way. And what we want to do is we want to make sure that the replacement wetland compares or is equivalent to the reference wetland. So what we do is we do a comparison between, you can see the arrows at the top here, a comparison between the reference wetlands and the replacement wetland to see how well it's working. Let me see if I can highlight this. This is going to be super clever. Yay! And then we want to do a comparison between the replacement wetland and the original lost wetland here. So really we need to have some measurements of that wetland before it was lost so that we can determine how well our replacement wetland is actually working. And so once we have these comparisons in place, we can take the ecological successes, which are down here, and the legal successes, which means that it needs to have that format that is required by the government. And when we put these two together, this gives us a measure of the overall success of that wetland. Okay, got to turn off the highlighter here. All right, so how is the replacement success measured? Well, you can have this ecological success. So that is, again, the comparison of the replacement with the reference wetlands. The legal success is the comparison of the lost wetland function with that of the replacement wetland. And then when you combine the two, then you get the overall success. However, as noted here, really it's often not the case where you take the two and you compare them unless this is actually a research study area. Okay, so what is the wetland success for reclamation typically based on? It's based on the function of the wetland and the ability of the wetland to retain that function over a period of many years, but it's also based on the size of the wetland that is lost. Okay, so for example, we would apply what's called a mitigation ratio to determine what the area of wetland that should be reclaimed or restored. So this doesn't have to necessarily take place at the exact location where the disturbance occurred. It can take place in another location, but as long as there is some restoration or reclamation of a wetland that occurs, this is what is required by the government. So the mitigation ratio is typically 2 to 1, meaning that 2 parts or 2 hectares of wetland area needs to be restored for every hectare of area that's been lost. And this ratio will change depending on the value of the wetland. So the more valuable the wetland is that's being changed or destroyed, the greater the area that has to be reclaimed. But generally, we want to try and follow this avoidance, minimize, and replace framework to wetland environments in Alberta as required by the Alberta Wetland Policy, but also the international agreements set up by Ramsar Convention for Wetland Management. The difficulty, though, is that a number of controversies can exist when reclaiming wetlands and trying to figure out what is actually successful reclamation. So the first question that typically comes up is, can wetland loss be mitigated successfully? How do you determine what success is? In the United States, for example, they've had a net gain of 8,000 hectares of wetlands per year. But in addition to this, 8,000 hectares per year of wetlands are also being lost. Okay, so when you take that and then you also add this mitigation ratio of 2 to 1, you're actually reclaiming 16,000 hectares of wetland areas. Okay, the difficulty though is you're reclaiming them, and we're always coming up with better methods to reclaim them and also better methods to measure this reclamation and the success. But it's difficult to determine whether we're actually losing or gaining wetland function when we compare the wetland that was reclaimed with the wetland that originally existed. Okay, so how do we assign a mitigation or replacement value for a wetland in Alberta? Well, we have to apply our knowledge of the value of the wetland. So here in this table, you can see a wetland replacement matrix. These are the values of the wetlands here from A to D. This is the value of the wetland that was lost, where A, I can circle it here, A is the most valuable wetland, whereas D is the least valuable wetland. And if we look at this column, I'll show you in green here. This is very clever. So if you look at this column, D, this is the increasing value of the replacement wetland. So this is basically what it costs or what the value of that wetland would be to replace. So here we can see at the bottom 1 to 1, a mitigation ratio, meaning that for every hectare of wetland that's lost, you need to reclaim 1 hectare of that wetland. So this is our lowest value wetland. Really, we don't care all that much about this wetland. Maybe the function of it is not great, or maybe there are a lot of these wetlands in the environment. But as soon as we get up to these level A wetlands, sorry, Finn's wanting fuss here. As soon as we get up to these level A wetlands, these are very valuable, and they have a replacement value of 8 to 1, which means that we need to reclaim 8 hectares of wetland, of an equivalent wetland, to every 1 hectare that is disturbed. So you can see why we would want to avoid disturbing these wetlands at all. They're very rare. They have high function in the environment. Okay, so the other thing to consider as well is that we have higher mitigation ratios due to the high value of wetlands because we expect that our reclamation strategies are going to fail. So we reclaim a much larger area, expecting that maybe if we reclaim, 4 hectares for every 1 hectare that's been disturbed and so on, maybe only 2 of those hectares will actually be functioning successfully in the future, or maybe it's only 1 hectare. So you can see that this is quite risky and also quite expensive as well. So in terms of the Alberta Wetland Policy or the Alberta Wetland Mitigation Directive, this is an active requirement for all wetlands that are disturbed, and they also need to be monitored as well. The difficulty is that we still are trying to figure out the best way to monitor them. So when you apply a mitigation strategy, you're really committing to replacing the total area of the wetlands. So, we might consider, well, we've disturbed 10,000 hectares of wetland area. That's a massive area. Or maybe it's only 10 hectares of wetland area. We have to consider the costs associated with this. So when we get into the public lands, these are all wetland areas between 1 and 12 here up to here. And the wetland reclamation costs associated with that can be anywhere between $19,000 or $17,000 and $19,000, and this is per hectare. So you can imagine the costs really add up when you're reclaiming a large wetland area. When we get into the public or all other kind of provincial lands, especially in the white zone, these are agricultural areas, these costs can be anywhere between about $17,000 and about $19,000. So clearly there's significant costs associated with this. The other cost is that needs to be incurred is when you compare the pre-disturbance function of that wetland with the post-disturbance reclamation. And on Thursday, I'm going to tell you a little bit about how to do field work and the costs associated with doing field work. To measure pre-disturbance and post-disturbance, it can cost you up to tens of thousands of dollars per wetland type. So, you know, you really need to consider these costs associated with the measurement and maintaining these measurements over time. Okay. All right, we also need to have a plan of the specific, measurable, attainable, realistic, time-bound wetland reclamation objectives and outcomes. So you're basically applying a wetland management plan to the wetland environment once it's been damaged or if it's been mined or changed in any way. And this needs to be approved by the government. And then you need to discuss all the projected impacts to the wetland feasibility plan, and you need to follow best practices. So for example, if you have a wetland that's been reclaimed and then you have in a maybe 2 or 3 years time you have a drought for 4 or 5 years, then you need to have a mitigation strategy for that and a plan for best practices. Okay, so clearly there's a lot of planning that takes place. There's a lot of legality within this type of reclamation, and there are certainly requirements for expertise in the wetland mitigation and replacement field of research and activity. So I'm going to give you an example of some monitoring work that I've done at some reclaimed wetlands in the oil sands region, and you can see here we've done a whole bunch of measurements. These are the measurements that have existed that we've done from 2006 all the way to 2016. So 10 years of measurements at all of these sites, and then you can see the sites, each of the different sites along the top. I think there's 12 sites. I can't quite recall, but I think there's 12 sites here. And so we were measuring a lot of these wetlands using plot measurements. So here, these are vegetation plot measurements, the top kind of medium gray bars at the sites. These were in the dark gray. These are all flux measurements. So we were measuring carbon dioxide and methane fluxes. And then in the light gray here, we also have satellite imagery for each of the summers of comparison. And from the satellite imagery, the measurements of the plots over time and also the carbon dioxide fluxes, we could determine how quickly these wetlands were coming back to their original status, whether they were going through kind of a rapid evolving or succession into upland forest. And we could kind of put together a plan or a framework as to how these wetlands would look in the future. And this is only after 10 years of data. So here, this is just an example. This is an image stack from 2006 all the way to, I think it's 2016 here, of normalized difference vegetation index, which is an index of canopy cover, and we can actually map the trajectory of growth of that vegetation over time. So this is one particular pixel, this bar here. Sorry, I can highlight it for you. So this bar here is 1 pixel over one particular time, and then this is the trajectory here of the vegetation growth over time. And we can do that for every single pixel in every one of these reclaimed wetland areas. Okay, another activity that is also ongoing, and this is I find this really fascinating, is the use of what's called a mitigation bank. So a mitigation bank is a wetland or a collection of wetlands that has been restored or constructed. And what you can do is when you disturb a wetland in one area, say for example, in the oil sands, or maybe you build a subdivision over some wetlands, what you can then do is you can then take the money that you would have put into restoring the wetland, and you can purchase the same kind of area that's required in the mitigation strategy within a wetland from a wetland bank. So it's basically like, it's kind of like taking money out of the bank to pay for something, but in this case, the bank is a whole bunch of wetlands, and so you're basically paying for the reclamation of wetlands in a different area. So this is the way this kind of diagram here is the way this works, and basically you have this development of that wetland environment here. The developer impacts the wetlands. And then what they do is they pay for some credit that goes into this construction of this mitigation bank here. Okay, so the mitigation bank builds up the wetland using the money that the developer would have put into reclaiming the wetlands in their local area. So then they receive some credit for the development of that wetland, which means that they can continue to disturb and develop on top of the wetlands in their area. This regulating agency here will go and they'll monitor that mitigation, that constructed wetland in the mitigation bank over time to give the developer the credit that they need to continue developing their houses or their construction over those wetland environments. So that's basically how that works. Okay, so we've talked quite a bit about oil sands reclamation and development of wetlands. How do we restore wetlands in agricultural areas? Well, in a lot of cases, it's actually kind of fortuitous because a lot of cattle farmers, and I'm sure you've seen these in the environment, a lot of cattle farmers will kind of put together these, or they'll dig out these holes for cattle to drink from. Here, as I've shown you with the arrow, I'm getting really carried away by this highlighter. It's absolutely fantastic. But they'll dig out these areas for cattle to drink from, and those dugout areas actually eventually become marshes or prairie potholes, and they have quite a similar function for the most part. And if you recall from your assignment, in the second image set that I gave you, there was a really kind of square or rectangular open water area that was dug out. And it's very likely that that area that was dug out there will also become a marsh. Now, even though we're seeing these dugout areas for cattle, there's some concern that these ponds may not be ecologically viable. They may not, over time, have the same ecology as our prairie pothole environment. So it makes us wonder, can we count these as reclaimed marsh wetlands. So just to give you an example here, in the United States, there's a project called the Wetland Reserve Program where farmers are funded to protect, restore, and enhance the wetlands on their properties. And so because the farmers are given money to do this, they're restoring large areas of wetlands that are on their farms that are also available potentially for cattle grazing. And so you get this kind of mixture of these dugout holes, which are for the cattle, and these kind of wetland environments that are all being protected together. In Canada, we have Ducks Unlimited. So Ducks Unlimited will come in and they'll restore your prairie pothole, your wetland environment for a 30-year period, a 30-year easement, which means that if you have an easement, it means that you have a legal obligation to continue to maintain that wetland over 30 years, and they can help you with this. But really, it just means that you can't kind of destroy that wetland. You can't, drain it or do anything else with that. So they'll also provide a variety of tax incentives to protect those wetlands and different grazing tenders as well. So this is a really great method to encourage farmers to continue to maintain their wetlands. And I know you can't answer this, but I was just wondering if you knew anyone who is currently working with ducks to protect their wetlands on their property. I know I had a student last year whose family had engaged in this wetland protection, which was really neat, and he kind of told everybody how that was working out, and it was working out really quite well. Okay, so another type of restoration that can be done is forested land restoration. And as you probably recall from swamps and these intermittent water bodies within forested areas, it's tricky to identify these areas, and it's even more tricky to restore forested land, wetlands, and some of these intermittent loss wetlands hydrologies. So over time, we've seen significant losses of forested wetlands, especially in southern Ontario, especially associated with the Great Lakes. But there is a real desire to come in and regenerate these wetland environments. The difficulty is that it can take decades for the trees to mature, and that on top of the intermittent hydrology of these wetland systems, it makes measuring their success really quite uncertain. We need to monitor these for a long time. So in Ontario, in southern Ontario, Ducks Unlimited Canada, or DUC, supplement the Managed Forest Tax Incentive Program by providing additional funds to landowners to hopefully reclaim their wetlands in their kind of their vernal pools and their forests and swamps. In this case, landowners that have a forested area are designated to pay 25% of their municipal tax rate for this area. So they can incur significant savings on their land taxes when they reclaim wetlands on their land. And this also protects, other vernal pools and swamps, because it provides landowners with the incentive not to develop those swamp areas. With regards to hydrological restoration, now this starts to become tricky as well, because we need to first determine the hydrological conditions before the wetland was disturbed, and then we need to have some method of establishing a measurement regime so that we can determine whether those processes are being maintained over time after the wetland has been reclaimed. So again, the idea here is to mimic the wetland environment previous to disturbance, okay? So this requires some hydrological measurements and assessment, and so you need to buy the equipment to monitor the inflows and outflows of groundwater and surface water, and these are usually piezometers. These measure kind of the pressure of the water and how the water moves up and down in the soil column, and also within a water body. Water levels can be measured more simply using kind of a staff or a ruler, and you can measure that by going out and checking the water levels each day or maybe once a week. But they can also be measured by electronic instruments such as piezometers. There's also an interest in measuring flooding and soil saturation. So to measure soil saturation, we use time domain reflectometry, which basically measures the conductivity of the soil and the current within the soil. If you apply kind of an electrical pulse through the soil, it can determine how saturated the soil is. And typically these TDR probes or time domain reflectometers, they're kind of two-pronged, and you stick them into the soil, or you can stick them horizontally as well, vertically or horizontally. And you have a data logger that measures the soil saturation over time. So you can do this for years perhaps, in order to see what the flooding and soil saturation regime is of that wetland. So finally, you need to understand the configuration of the topography that contains the wetland, whether the water, if it's a marsh, if it is maintained year-round, or if that is kind of an intermittent marsh, if it dries up at some point. Sometimes you need to excavate the area because it may not have contained a wetland to begin with. So recall that we're talking about areas that have been disturbed, but also these areas that when you reclaim them, you disturb and then you reclaim the same area, or it might be completely building a new wetland in some other location. Obviously, if you have kind of this kind of dipped topography, then you get to you position the wetland within the water table, which ensures that maintenance of water. Okay, so if we're restoring hydrology, we also need to consider the hydrologic conditions of that area. So with regards to a disturbed area, we want to know what the topography is of that species. We also need to understand the slope. So is water going to drain into that wetland? And then based on the hydrology, the vegetation species that are going to exist there. So topography is important because the slope determines how far the substrate is from the water. So here I can show you that if we have a vastly sloped surface here, you might have a very high water table, which would indicate certain species of typha that could grow along the wetland edges. Here, certainly if it's very deep, you're not going to have vegetation growing within the open water body. But if you have a much kind of flatter topography with less of a slope that we can see right here, your water table is still going to reach the surface, but it's going to be a lot shallower. And so you might have a lot more vegetation biodiversity. You'll have the growth of aquatic vegetation within the wet area, and then a variety of marsh grasses, typha, phragmites as well, growing along the sides. So this is important because it determines the different plant species but also the type of soil that is going to start to regenerate and develop in this area as well. So remember that hydrology is connected to the type of plants that grow, but also the accumulation of biomass through mortality of vegetation over time and the development of that thick kind of organic layer. Okay, so the ability to maintain this plant community depends on hydrology. If it's always wet, if you have this large open water body, then it is less, then it might provide less of a habitat for certain types of animal species. Perhaps you don't have the same amount of vegetation. If you have less inundation, if you have saturated soils and shallower water, then you're going to have many more plant species. Okay, water quality, again, is also very important. Recall from our biogeochemistry lecture that the chemicals in the water can result in a variety of different plant species growing in them and also alter the ability of that wetland to take up nutrients. So chemicals in the surface water could result in, if you have a lot of nutrient runoff into the wetland, it could result in poor water quality leaving the wetlands. So this wetland could become like a mine for minerals and other contaminants, which you don't want. The water quality could change the vegetation characteristics. So for example, if you have a wetland that's located near a road, that wetland can accumulate a lot of salt over time, which would change the species that are adapted to a more saline environment. It can also cause invasion of invasive species such as purple loosestrife, and this is probably one of the reasons why if you drive down the 401 highway just east of Toronto, then you can see a lot of purple loosestrife development all within kind of those low-lying ditches along the side of the highway. Okay, so if the water quality is affected, the soil quality will also be affected. You can get differences in porosity of the soil, so the ability of water and nutrients to flow through the soils. And then this also affects the hydrology when you compare a natural reference wetland versus the one that's being reclaimed. So for example, if the porosity is changed, if a soil is more compact because you're in the process of digging out that environment, then the hydrology will respond differently to the soil characteristics. More water will sit on top of that wetland environment. So we want the organic soils to promote growth. We want it to retain moisture, and we want it to increase in that organic matter. Okay, organic soils are also important because they reduce evaporation, because they hold the water in the soil. Remember that cation exchange process. They also reduce runoff and loss of soil and erosion. Okay, so in addition to the soils and the water and the movement of chemicals and nutrients into the wetland environment, we then need to consider the handling of plants. Once we have formed our wetlands, we'll want to plant different plants around it to maintain it, to grow that habitat. So it's also important to recognize that we want to grow the plants that are most appropriate for the environment that we're reclaiming. So we might add plants that resemble communities that are similar to local wetlands, but we also have to recognize that, you know, when you get to the outer boundaries of the wetland environment, there's going to be some unique community establishment, this idea of self-organization of the wetland that occurs over time. So you might plant a species that you're really keen on, you're really excited about, but over time that species cannot compete with other species, and so it dies off. So we need to recognize that wetlands are going to do that over time, and we have to balance that idea of allowing them to do this, but not having regeneration of plants that we don't want. So in 1986, Garbish suggested that plant managers first use herbaceous species that rapidly stabilize the substrate and have value for fish and wildlife species. Then we want to use species that are adaptable for a range of water depths. So this is ensuring that the species are going to survive when that wetland's flooded, and then when it dries out, other species come along, and we can ensure that that wetland will continue to be successful. Third, to begin with, we want to make sure that this is an ideal habitat for foraging. You're growing and you're developing your wetland. The last thing you want is to have geese or muskrats move in and then completely graze out your entire wetlands. So we want to avoid those delicious vegetation species that a lot of animals and birds will want to eat. We want to avoid using species that have a low success rate over large areas. So we want to plant with species that we know will be successful. We may not want to introduce, really kind of cool niche species that just might not last. Okay, so this is a diagram of the monitoring time versus the effectiveness of the function. So here, I'll just highlight this. This is your monitoring of the wetland over time, and this is your increasing effectiveness of the wetland function. And the blue dots represent your natural reference wetland over time, and you can see that the variability varies a little bit. Maybe sometimes the function is better than some years, sometimes it dips down and is lower, but generally we have a stable average for this wetland environment. It's a natural wetland. We expect it to continue to be successful, all else being equal. Now, this in the orange here, this is our disturbed and restored wetland here, and you can see over time that, as we continue to monitor over a period of years, the function of the wetland slowly improves until, maybe 20 years later, that wetland has reached maturity. But what's interesting here, and this is a study by Cantrud and others, this indicates that for this particular wetland, the wetland kind of developed in its function and then reached a stable point where the function didn't continue to improve. And the point that these authors are making is that the restored wetland function never really quite reached that of the natural wetland. So there's a gap there. You're not getting that kind of the same function of that wetland. So you're not getting necessarily the same ecosystem services. So this is a particular case. This is not necessarily for all wetlands, but it was kind of an early study of how the function of these wetlands would change over time. Okay, I wanted to show you this other case study of prairie wetland communities and their recovery, and how, not all wetlands are created equal. Some wetlands recover at different rates following hydrological restoration. This is kind of a more recent study from 2016. So here we're getting better and better at our wetland reclamation, but we're also getting better at monitoring and managing these wetlands. So what they did was they looked at the recovery of hydrologically restored wetlands over time using water chemistry, so measuring the chemistry of these wetlands, and taxonomic shifts in vegetation communities. And their study area is right here. I'm just going to circle that in green on the map. Here's our study area, right? I'm sorry, it's red. Surprise, surprise. The study area is in southern Saskatchewan. And here in B, you can see all of their kind of wetlands that they examine right here. Okay, this time I will do it in green. Here's all of their kind of reclaimed and referenced wetlands, and they're all different ages since restoration. So you can see that the authors examined 24 wetlands. They have wetlands that have been recently restored, so 1 to 3 years, older restored wetlands, 7 to 14 years, and then natural, never drained wetlands. And what they find is that within 10 years, previously constructed wetlands resemble natural wetlands in all cases in terms of phosphorus, carbon dioxide. See, this is the period of time here from recent to older to natural. So I'm going to draw this out. The similarity between the latter two indicates that the older restored wetlands are very similar to the natural ones. In many cases, phosphorus, carbon dioxide, and salinity, pH is still a little bit different, but it takes 10 years to be able to achieve this in all of these wetlands. Okay, so now that we know what is required to monitor these wetlands, how do we actually create and restore these? And you can see this image here of this dugout. It's fenced. They're applying all the right rules. Maybe they haven't vegetated it yet, but it's dug out to form this deep water marsh environment. Here's Finn. Here, Finny. I just thought I'd take a little break to show him to you. Okay, well, he's gone now. Back to the lecture. So the first thing we want to do is we want to define our goals for wetland creation. So the first goal is that we might have could be habitat creation. We may want to create a wetland to control pollution. We may want to create it for wastewater treatment. So in all cases, what we want to do, though, is we want to maximize ecosystem longevity. We want to maximize the efficiency of this wetland in its ability to, create habitats, control pollution, and so on. And we also want to minimize the cost because this is going to be a costly endeavor. So we need to determine what's most important. So to minimize the cost, we want to place our wetlands in the landscape, and typically we want to put this in an environment that is going to encourage the maintenance of the wetlands. So maybe building a wetland on top of a hill, where you have this kind of rounded surface isn't the best idea. We want to perhaps place our wetland near the edge of a river, place it in a dip in the topography such that it can continue to receive water naturally. So if you place a wetland beside a river, this provides a natural flooding potential from the river to wash into the wetland. Rivers also will deposit sediments and various nutrients. And then over time, the flood waters will go back into the river so that that wetland isn't, eternally flooded. In addition to this, natural levees, which I'll circle here, natural levees are really great because they can allow the water to go in and then seep back out over time without the requirement for minimal development. If you've done any digging with an earth mover, renting those things or owning those can be quite expensive. If we are creating wetlands that we want, where we want habitat creation, then we can put our wetland in a whole variety of different environments with minimal construction. For example, we can put our wetland on the edge of a river which has natural flooding, and we can redirect the water to go from the river into the wetland and then back out again. We can also use a pump to pump water into the wetland to ensure predictability of hydro periods. If you managed to watch the video in the last lecture, they were talking about kind of slowly raising and lowering the water levels to mimic the natural variability in the hydro period and the climate. Okay, other methods for placing wetlands on the landscape could be to put a variety of wetlands upstream. You can position them along small stream sections upstream of a larger downstream wetland, and by providing kind of that directionality of water to move into those smaller wetlands, then you're maintaining multiple different wetlands at the same time. Other methods include adding a drain pipe. So here you can see this tile drain pipe here. A tile drain will move water from like an agricultural area into kind of a low-lying area, and you can actually put or plan to put your wetland into that low-lying area, and the tile drain will just ensure that water keeps moving into that wetland through lateral movement. Okay, so when selecting a site, you want to meet the objective of constructing the wetland at as low a cost as possible, but also to ensure predictability of hydrological performance and long-term maintenance. If you add a pump to your wetland where you're kind of changing the hydrological regime or the hydro period, then this can be quite costly over time. So you want to ensure that you're not, your solution is as inexpensive as possible. Some things to keep in mind: it is easier to restore a wetland than it is to create one. You also need to account for the current land use and future land use plans of the area. So you don't want to build a wetland in an area that may be being encroached on by housing development. Maybe this will be developed in the future, because then you're just basically throwing your money away. Other things to keep in mind: take a look at the hydrology of the area, including the groundwater. So if you use Google Earth, you can kind of see these dark areas in the landscape here that might indicate that there are wet areas in that area where you want to reclaim the wetlands, here and here, as well as here. So this indicates that there's some soil saturation which would make it suitable for building or reclaiming a wetland. Right, and I even put arrows there, which I forgot about. Great. So we can also add other areas where sites are inundated with water. If you've got these dark patches, or you can actually see that kind of black water area there, then you can use these as indicators for where to put your wetlands. It's also a good idea to dig a hole, just a small hole, with your shovel, and look at the soils, the texture. You can look at whether clay exists in that area, the permeability, and so on, to see whether that wetland would be maintained in this environment. Other things to keep in mind: determine the soil chemistry for water entering the site, as well as the soil chemistry for the environment. This will be important for the planting and maintenance of vegetation. Look at seed banks. So you may not need to plant all the vegetation that you want to plant. You might just be able to rely on what's already there and the potential for success of that wetland. The infrastructure that is needed. So do you need to provide electricity if you've got a pump? Do you need to have some road access? Do you need to provide certain types of soils for that environment? And then if you want to buy land to build a reclaimed wetland, what does it cost? You know, you can't necessarily go in and say, well, I'm going to reclaim a wetland in this area. You may need to buy the land. Okay, if you want to attract wildlife, you should make sure that your wetland is located along an ecological corridor where, you know, for example, migrating birds would see the wetland and want to land in that wetland and use it. Your need for site access, this is similar to 8. If you can't get into the wetland, then it's going to be very difficult to monitor it. You want to provide adequate amount of land area to meet the objectives. If the land area is too small, then you might not reclaim the area that is required to reclaim according to your 2-for-1 ratio. Okay, other considerations, groundwater flow should be predictable. You should be able to ensure that the groundwater is adequately available for the wetlands. Location near a river is good, but you might have dry periods, so this also needs to be considered. Surface runoff from small streams, this is useful, but can maybe not be so predictable if the stream is ephemeral, meaning that, you know, in the summer the stream disappears, so maybe the wetland does as well. So it's most optimal to put wetlands where they used to be, but you know, you might have some modification of hydrology. Okay, so to retain that hydrology, those saturated soil conditions within a previous wetland environment, what do you need to do? Well, the best thing to do is to slightly excavate the land and build up levees to maintain that water. And you can see, if I circle it here, this is a levee here that was built up, and it ensures that the water is kept within that wetland environment. It's also cheap to use excavated soils to build the levee, but sometimes if you do this, the levee can actually break. You can actually get seepage of wetland water into the surrounding environment. So it's really better to kind of dig down into the environment. Okay, so excavated depression without building the levees necessarily. Okay, so what are some of the mechanisms that we can use to maintain the hydrology of the environment? Well, there needs to be some device in order to control the water level. And the first one is the most simple. This is called a drop pipe. And drop pipes are basically, you can see here, here's a drop pipe here that's installed within the wetland environment. As the water level here gets too high, it will fall into the drop pipe and it will maintain that water level. So the water doesn't go up and down, it just always kind of, well, it can go down, but if it rises to a certain level, it can only get to that level before the water is evacuated away. So this typically doesn't really allow for many water level changes and is really the least sophisticated. The second one is called a flashboard, and you might see these in some wetland areas. I think in the Helen Schuler Park and the Elizabeth Hall wetlands, we have this flashboard system, which is like a kind of a vertically placed cauldron and or culvert, and so you can add wood to it here, which I've highlighted, and the wood can be removed as required to rise and lower the water level. As you take wood out of the system, then the water level can go down, and it runs out through this pipe here to a discharge pipe. As you build the wood up, then the water levels would be higher because you need a higher water level to go over top of that wood surface. This is quite flexible. However, they are simple to remove. The wood is simple to remove, and so they're prone to being vandalized. You could also use what's called a full round riser, which is a combination drop pipe and flashboard. And this is secure, but they're also kind of more expensive. And so here you have kind of a guard for beavers. With regards to the flashboard, these can be vandalized by people, but they can also be vandalized by beavers because beavers can take out the wood as well. But in this case, you have a beaver guard, and then water will go in and it'll rise up through the drop pipe here. Let me see if I can draw you an arrow here. The water level will go in here and it will rise up into this, into the flashboard, and it'll overtop the wood that's in it, and then it'll flow out once the water is too high. So again, we can raise and lower the wood, the water levels using this method as well. Okay, so I wanted to just show you this little study. This is a study that was conducted by an undergrad student at the University of Alberta, and she did a really kind of neat study on kind of the accidental creation of wetlands within reclaimed oil sands areas. And you can see here on this figure 3 areas on the map that were mined areas that were reclaimed. And over time, as they kind of put soils down onto these mined areas, the soils settled and created these depressions. And those depressions created these accidental or these opportunistic little wetlands, which nobody expected to form. And they ended up being highly biodiverse. So she wanted to figure out why, what were the driving mechanisms, what caused these wetlands to form. And to do this, she put in a series of these transects, which are marked by A and A prime, B and B prime, and C and C prime. And then she measured kind of the elevation of the environments as well. So the overall objective, as I mentioned, of the study was to determine under what conditions could the wetlands formed, and then could they reproduce these conditions such that they could encourage more wetland formation like this. So she found that most of the wetlands formed in valleys, so that's something that we would expect. But she also found that they formed on the tops of slopes and in flat areas, and especially if the surface wasn't sloping. In addition to this, the area or the areas where the wetlands form had to have high solar radiation. So this is kind of interesting because if there's high solar radiation, you'd expect this wetland environment to dry. But what she determined was that where you had high solar radiation was also indicative of low vegetation cover, which indicated that wet soil environment. Okay, so moving along, I'm almost done here. When we're considering building wetlands, we also need to consider that hydric soil. So remember, the glaying that we talked about in the soil would be a good indicator of that hydric soil condition. The advantages of hydric soils is that it's an indicator of a currently or previously wet conditions. That these soils may have seed banks that are appropriate for the growth of vegetation, wetland vegetation in the environment. And finally, that these soils typically have the chemistry that is required to enhance wetland processes. Okay, so the last part of this is to introduce vegetation to this environment. And this really depends on the type of wetland, the region, and the climate. So when we're talking about marshes, typically the vegetation that we would use includes bulrushes, cattails, sedges, floating aquatic plants. Submerged plants may grow over time, but not at first because of high turbid conditions. Within forested wetlands and swamps, cottonwood are a really good species. Certainly in Lethbridge, we have lots of these: balsam poplar, black spruce, tamarack, larch, white or Alaskan birch, green alder, speckled alder, willow, bog birch, blueberry, Labrador tea. And within bogs, if we are going to develop a bog, black spruce, tamarack, blueberry, creeping snowberry, dwarf bog, crowberry willow, leatherleaf. Certainly you can put down sphagnum soils as well. So when you transplant vegetation, you typically want to take the roots, the rhizomes, the tubers, seedlings, or any mature plants and put them into the soil. You can also import soil with its own seed bank, and then you can allow that wetland to self-generate, to self-design over time. And you can also plant at a range of densities to ensure rapid colonization. So here you might want to plant fairly densely to reduce the invasion from other plant species, and especially invasive plants, which typically move in as soon as you develop an area. And then finally, you want to transplant whole plants with 20 to 30 centimeter stems, especially in the spring when the soils are cool, so that the plants can get the most moisture as possible, compared to in the summer when it's a lot drier. We also need to allow for this idea of natural succession. So this means that the wetland's low maintenance. We don't have to constantly be, doing things to it. We can allow the native species to regenerate. We can allow succession to occur, and this will allow a result in the wetlands self-design, so species eventually sort themselves out. If we want, we can develop what's called a designer wetland, where we plant specific species, and then which species survive indicates the success or failure of the wetland. Now, clearly this method is probably a little bit more detailed and expensive, but it would give you a wetland that maybe is something that is more physically appealing to yourself. Okay, so here is a study on the success of reclaimed wetlands, and this in black, this shows you, this is the number of mitigating wetlands over time, and this shows you black is successful, dark gray has limited success, gray is failure, and this is incomplete. So these are mitigation wetlands that are successful versus those that are not very successful and fail over time. And you can see that really in certain conditions, there are lots of failures that occur. And over time, maybe we have a transition to excessive open water in some of these environments as well. So this is why this ratio, this 2-to-1 or maybe 4-to-1 or 8-to-1 ratio is important, because even though we have lots of successes, we have also lots of failures. And if you have an open water area that becomes predominantly open water, that is also considered a failure. Okay, this is one of my last slides. This is a study of ecological success of biological structures and biochemistry by Marino Matos et al. From 2012. And this shows you, this is the number of observations over time. And this is the response ratio. So this is kind of your biological structure, and this is your biogeochemical process. And we can see that over time, the biological structures were 26% lower in reclaimed areas, which represents the green line, whereas when we look at carbon dioxide uptake, even though it can take a lot of time, that carbon dioxide uptake will basically even out to our response ratio, our biological structure. Okay, so some of the take-home messages from this work, they found that the environment was important for the rate and degree of recovery of the wetlands, that restored large wetlands larger than 100 hectares and warm wetlands recovered more rapidly, that small restored wetlands and wetlands in cold climates recover more slowly, which makes sense. Wetlands with riverine and tidal exchanges recover more rapidly. Wetlands that recovered in depressions recovered more slowly. And finally, restoration does not recover original levels of ecosystem function even after many decades. So I want you to think about what could be the problem associated with this restoration, why these ecosystems just may not be recovering. Okay, so with regards to success, we need to measure success over a significant amount of time. Often it's the whole career of some people, 15, 20, 30 years for freshwater marshes. It can take decades to hundreds of years of monitoring for forested wetlands, and this is why they're so complex. We're really only now seeing the successes of our learning from 10 to 20 years ago. So hopefully all of this effort that we're putting into this is going to really improve how these wetlands function in the future. Okay, just to leave you with this final slide, I'm amazingly over time this time and so much under time last time, probably because I wrote out what I was going to tell you last time and I talked freely this time like I would do a normal lecture. But Mitch says, with regards to engineering versus science, ecosystem restoration as currently practiced throughout the world is done by practitioners who have little experience in design. Scientists study systems, but they do not design systems, and by engineers who do not appreciate the capabilities of ecosystems to self-design. Engineering is a field devoted to removing uncertainty and controlling natural processes. The approach of many restorations is restoration by committee that results in projects that are less successful than anticipated or over-designed by engineers with unsustainable technology. So this is this idea that we really just need to let wetlands do their thing. Okay, so this Thursday, I'm going to show you just some photographs. I'm going to talk you through fieldwork, even though we can't actually go out and do fieldwork, which is a bit of a shame. So I'll show you a virtual demonstration with some photographs. I'm going to try and set up a couple of videos and methods of setup, and then we'll talk a little bit about wetland policies and laws in Canada. Okay, bye for now.